So, Unit 6 is all about applications of trig and a little bit of review. We're going to start off by splitting apart the first section into 2 days. The first half is all about these things called sectors, and by the end of the lesson, we should be able to solve problems that utilize sectors, specifically looking at two physical attributes of sectors, its area and arc length. Well, first things first, if we're talking about sectors, we should probably know what the heck a sector is. Well, let's take a look at the definition here. I suppose this is less of a definition and more of an explanation. But a sector involves a circle. Now, hopefully, you can sort of assume that this is a perfect circle, right? In layman's terms, a sector is just a part of a circle. I guess it's so important we can write that down. It's a slice or a part of a circle. But it's not any slice, right? You can't just be a rogue, pizza maker and make slices this way. Who cuts a pizza this way? Typically, when we slice a pie or pizza, we usually do it from the center. So when you slice a wedge of a circle from the center, that is what we call a sector, right? So a sector, made it look like a right angle. It doesn't have to be. Oops. So a sector is just a slice or a wedge from a circle. Doesn't necessarily have to be 90 degrees. Let's do this here. Now, what are some names? What are some parts to a sector? Well, every single sector is defined by its central angle. Well, what is the central angle? It is the angle measured by or at the center. Sort of a no-duh definition. So take a look at this angle here. See how I'm measuring about the center? So we call that the central angle. And let me go ahead and highlight the whole sector. This guy here is the whole sector, and hopefully you guys can agree that the whole sector covers this part of the circumference. Not surprisingly, the length of the circumference that a sector covers is called the arc length. Now, there are formulas to calculate these values, but I want to go beyond the formula, right? I want us to understand the idea of a sector. And this is sort of like the big idea. We can see that a sector, here's the sector. It's just a part of the full circle. So because it comes from a circle, all the physical attributes of a sector come from the physical attributes of a circle, right? So how should we word this? I guess we should just write down exactly what I said. The physical attributes of a sector comes directly specifically directly proportional, comes directly from the attributes of the circle it came from. Now, here's what do I mean by that? Well, let's just talk about some hypotheticals. Suppose I had a full circle, right? Now, this full circle has a set area and a set arc length. Let's say this circle here, right? Let's just say that this area is, 2 units squared, and I take a sector that is a quarter of a circle. Well, I hope it makes sense that if you take a quarter of a circle, you've taken a quarter of the area and a quarter of the circumference. If my sector is half of the circle, I've taken half of the area, half of the circumference. If I took a third of a circle, the area is a third of the whole area. The arc length is a third of the whole circumference. So it's not that hard to calculate the area and arc length of a sector, but we have to figure out how do we calculate the proportion that the sector takes. Well, here's a couple of ideas. Recall, a sector is defined by its central angle. Right. A full circle has 2 pi radians, or 360 degrees. Right. So if a sector is defined by its central angle, this guy here, this little sliver, but we know that the full circle, oh, come on, little technical difficulties. There we go. And a full circle is 2 pi radians or 360 degrees. Therefore, the proportion the sector is to a full circle is its central angle divided by 2 pi radians, or 360 degrees, depending on what system you're in, right? With this, we can basically build formulas, right? So let's talk about the first easy formula. Let's talk about arc length. Again, the arc length of a sector is just a part of the whole circle's circumference. Now, the letter that we typically use for arc length, don't ask me why, it just is S, right? I suspect it's because the way the arc length was originally defined is with adding up a whole bunch of little lines. S stands for sum. That's just a complete conjecture on my part, though. Right? So the arc length of any sector is the proportion of the sector times the circle circumference. I hope that makes sense. Again, if the sector is half of a circle, then his arc length should be half of the circumference. If the sector is a third of a circle, his arc length should be a third of the circumference. Well, as stated before, to find the proportion of the sector, it's simply the central angle divided by the total amount of angles. Now, let's suppose that we're in the radian system. That's 2 pi times the formula for circumference. So we have to remember from geometry that the formula for circumference is 2 pi r, right? And then hopefully you guys can see that the 2 pi's cancel out. Therefore, we have the formula S equals theta r, right? Where r is the radius, theta is the central angle. Now, we developed this formula using radians. So you can only use this formula here if your angle's in radians. You can do the same thing for degrees. You can come up with your own formula for degrees, but all you got to do is simply divide by 360 instead of 2 pi. But I'm going to leave that as an exercise to yourself. Or if you ever had a degrees problem, just convert the thing into radians. So for example, find the length of an arc of a circle with radius 10 meters that subtends a central angle of 30 degrees. Subtends is just a fancy math term that means covers. Right? So I'm not going to do an accurate sketch because I can't, because I don't have a protractor here. Do I have a protractor? Nope, there's a ruler. No protractors. Maybe. Nope. But I'm going to approximate. Right, so here's the center. So basically what it says is if you carve out a wedge of a circle where this is 30 degrees and then this is 10 meters, how long would that arc be? Right. Well, we have a formula or we have an idea, right? So I'm not going to use the formula. Even though the formula is nice, I'm not going to use it. The idea is that the arc length is just a proportion of the whole circle circumference. Well, I know that the arc length is the proportion of the whole circle. Well, what is the proportion of the whole circle? We have 30 degrees over. Now, since they gave us degrees, we would have to use, well, degrees, right? 360 times the whole circumference. Now, this is something you need to memorize. You need to know the formula for the circumference of a circle. 2 pi times r. And that's it. Just do math. 3 over 360, what's that, 1/12? Times, what's that, 20 pi? And that will simplify to 20 over 12, reduce it by 4, 5 pi thirds meters, right? So that is the exact length of this blue arc. Right. And notice I did it using pure logic. I didn't have to convert to radians, and I didn't really need to use the formula, although the formula is nice to know. You should memorize it, but it's super duper easy. Now, typically with these problems, with any problem that's based off of a formula, 9 out of 10 times the problem will give you will give you all but one variable that you have to solve for. So this was a pretty straightforward question. They gave you an angle, it gave you a radius, boom, find the arc length. The only way, and it's not that difficult, the only way I can make this harder is give you different pieces of information. So for example, a central angle, theta, in a circle of radius 4 meters is subtended by an arc of length 6 meters. Find theta in radians. Gee, they give me information about arc length. Maybe we should use the arc length formula. Do note here that they said find theta in radians, so that means we have to use the radian version of the arc length formula. And the radian version of the arc length formula is S equals theta r. And then you just plug in the information they give you. Radius of 4 meters, well, duh, that's r. Arc of length 6 meters, no duh, that's S. So you just plug everything in. S is 6, theta is theta, r is 4, boom, you solve for theta. Theta equals 6/4, which is, what, 3/2 radians, right? So theta is 3/2 radians. Radians don't need to have pi in it, right? Radians is a pure number. That's why mathematicians like to use them. The other physical attribute of a sector is its area, and the idea is 100% the same idea as arc length. The area of a sector is just a part of a whole circle's area. So area equals, how do I calculate proportion of a sector? It's its angle over the total amount of angles, which will stick with radians, 2 pi, times, now since I'm interested in area, not arc length, I need to use the area of a circle formula, right? Let me go ahead and write down the idea. So area A equals proportion of sector times area of circle. So that's going to be central angle over whatever the total angles is, we'll stick with radians, 2 pi, times area of a circle formula is pi r squared. So here in this case, the pi's cancel out. So you get theta r squared over 2. Most people, however, they like to write it like this: 1/2 theta r squared. Again, r is the radius. Theta is the central angle. But the more important thing is it must be in radians, right? So this is an important formula to know. Again, you can memorize this formula, or you can always build it when you're doing the problems. Just remember, area is a part of the whole circle. So for example, suppose I ask you to find the area of a sector of a circle with central angle 6 degrees if the radius is 3 meters. Right? Again, they gave it to us in degrees. We can go ahead and convert this guy. We should know that 6 degrees is pi thirds radians. But let's just pretend that I'm too lazy. I don't want to convert. But oh no, I can't use this formula because this formula only uses radians. Let's use pure logic. I note that the area equals the parts of the sector to the whole circle. So they gave me the central angle. So I know that the proportion is the central angle over the total angles. Since we're in degrees, I'll use 360. And since I'm interested in the area, that's what the problem is relating to, I'm going to use the area of a circle formula. Pi r, which is 3, squared. And that's it. You're basically done. You just got to do math. So 60 over 360, what's that? Is that a 6? Times, 9 pi. So that's what? 9 6, which is 3 halves pi meter squared, right? So I hope dealing with sectors is going, blast from the past of geometry. Hopefully it's you guys find that it's super duper easy. Yeah, there seems to be complicated formulas relating to it, but in all honesty, it is pure logic. Anything involving sectors, area, arc length, it's just a proportion to the whole circle. Good luck.